as some of you have noticed, Prasad has walked from Friday to today because Arvind broke his toe, so he'll speak on Friday. One more schedule change for today. Nikhil Devanur couldn't come for some family emergency, and so Anupam Gupta will be giving a talk at 11:30 in place of Nikhil. And we'll figure out the schedule change later on. On Wednesday morning, Moran Feldman's talk will be replaced by a new bookbinder on the same, roughly the same area. And those are the 3 changes so far. And for tomorrow evening from 4:30 to 5:30, we're planning on having some lightning quick talks for 7 minutes. If you're interested in giving such a talk on open problem or a short result that you want to highlight, please send an email to the organizers, myself or any organizers. My email address will be chekuri@illinois.edu or at gmail.com. Okay. That's it for now. We want to thank Simon Institute, Alistair Sinclair, the staff. Peter Bartlett has taken over from Alistair, and the general program organizer. And our first talk today is by Prasad Raghavendra on the power of sum of squares for planted problems.
Thank you. Thank you for the invitation to speak here. And thanks for coming out this early in the morning on the first day. I barely made it. So today I'll talk about the power of sum of squares for detecting hidden structures. And this is joint work with Sam Hopkins, Pravesh Kotari, Aaron Potechin, Sleel Shram, I think, who's here, and David Steurer. Okay. So although we'll be talking about sum of squares, the main result will be about sum of squares, and it will be about hidden structures. The sort of the theme which I like about this work is really slightly more broad. So here's a linear program, and all of you might recognize immediately that this is a linear program for the maximum clique in a graph. Okay, this is a linear program for a maximum clique. And so when we want to understand the approximation given by this linear program, the natural lower bound technique is to produce a independent set. Oh, sorry, I meant maximum independent set. Yeah, thanks. Okay, so this is a maximum independent set, and okay, when you want to understand the approximation given by this program, the natural way to prove a lower bound would be to construct an integrality gap instance. And what would an integrality gap instance be? That would just be, I guess at the first cut would, for example, you could pick a triangle and show that the value of the LP is 3/2, whereas the optimal solution is only 1. So that gives a gap between the linear programming optimum and the optimal solution for the graph. Now, this is a this is a lower bound, but it is always a little bit unsatisfactory when at first, because in some sense, if you run the rounding algorithm on the integrality gap instance, you get a very good approximation, much better than the one given here. So in terms of rounding, it's not really a gap, because there is a gap between the LP and the opt. The loss incurred by the rounding is actually makes it comparable to opt. So in that sense, it's not a hard instance. And moreover, an obvious quip could be, hey, this is just one instance. How hard can it be? Let's just add a condition in our algorithm. Say, if you see a triangle, output 1. So really, when we want to say that this problem is hard, what we really want is a distribution over instances, right? A distribution over not just one instance, but probably many instances, and ideally a distribution over instances, all of which exhibit this sort of a gap between the LP and the opt. And even even that is actually not concrete evidence, like concrete experimental evidence. If you wanted to give concrete experimental evidence that the problem is hard, if I just gave you a distribution of integrality gap instances, it's somewhat unsatisfactory because maybe someone could quip, maybe there is some pattern among this distribution of instances which we don't see, but if somebody who sees this pattern, maybe the sum of the degrees of the first, second, and third vertex actually tells you that it is from this distribution, and that gives you an opt value on the opt. So therefore, what would really make it a satisfactory lower bound would be if you had a pair of distributions of instances which have different values for maximum clique, and they are somehow computationally indistinguishable in in all the ways that we try. So, and this is not a new concept. It's fairly well known. So, for instance, this is a very natural distribution over instances. So you have two distributions for the maximum clique, maximum independent set. I think I made it clique here. Yeah, it's a clique. So for the maximum clique problem, in one distribution, you just so this is the no case. In the no case, the graph just looks like a random GN half graph. Every edge is included with probability half. And we know that the clique size or in this graph is at most order log n with very high probability. Okay, the opt is order log n over here. And another distribution, which is essentially you sample a random graph of with GN half, and then you include a clique of size k into it. So this is a yes case. So this is just, you have GN half. You sample GN half and pick a random subset of size k inside it. And you include all the edges inside S into the graph. So make S a clique. So this is another graph. Now this gives you two distributions over instances. And the nice thing right now is that these distributions seem to give some concrete experimental evidence, you could say, of the fact that clique is hard. I mean, of course, there's much stronger evidence, but why am I looking at this? But you can construct much harder distributions which are indistinguishable for clique. But this is a very simple example of two distributions which we know and we expect to be computationally indistinguishable, in the sense that it's not just about LPs or SDPs. We expect that, if you take the degrees of these vertices in the graph and you compute the parity of all the degrees, they should be similar and so on. Although we don't know how to prove all these facts, we expect these to be true. Okay, and so this would be a nice sort of starting point for integrality gaps or lower bounds for problems. Two distributions which are indistinguishable. Okay, and and this is again not new. There's a lot of work on LP and SGP lower bounds for planted clique problem. But one thing that was always a little bit disappointing was that we always had the following issue, that if you want to prove that, let's say, linear programs, or let's say linear programming hierarchy doesn't solve this, cannot distinguish between these two distributions, the way we would go about proving that is we would prove that the no case is a distribution of integrality gap instances. Meaning, we would prove it the following way. We would say pick a random graph G from the no case, which is just the uniform distribution over all graphs. And then this is the no case, and then we would like to prove that the LP value, let's say the SDP value in this case is high. We'd like to prove that SDP opt of G is large. Let's say it's much larger than log n. Okay, and then the strategy would be, now we have a random graph, and let's just construct feasible solutions for the SDP, for this graph, construct a feasible solution for the SDP. Okay, this would be the approach. Now, for this graph, for G. Okay, and this would be extremely subtle, because the SDP has many, SDP or the linear program has several equality constraints, several inequality constraints, and many different constraints that we would like to satisfy in order for the solution to be feasible. But now we just have this one fixed random graph we're working with. We just got one random graph, and we need to construct this feasible solution for the SDP. And this exercise would be a little bit tricky, but moreover, what would be disappointing about it is we started with this situation where we were interested in whether we can distinguish between these two distributions, and this was a sort of our beginning evidence that this problem is hard. But right now we have thrown out all of any information about the planted distribution. Right now our problem is we just got a random graph, and we would like to construct a feasible solution for the SDP or LP. So this, the key disappointing factor about this is that the planted distribution, the indistinguishability of the planted distribution, the uniform distribution, cannot be exploited in this strategy yet, because we just got a random graph and we need to construct the SDP solution. And so this is what was basically the approach towards many of these lower bounds until this recent beautiful work by some of our co-authors and others. So it's Barak, Hopkins, Kellner, Kothari, Moitra, and Potichin. So they proved essentially a log n round integrality gap for SOS integrality gap for planted clique. But from me, the most important idea which they came up with is this thing which they call pseudocalibration. And this is a very pseudo-calibration. This is a very beautiful idea.
So what's exactly the statement? That in so many rounds, what do you...
It's in log n rounds, you cannot get n to the half minus epsilon.
Is the integer programming formulation, they all only deal with this integer programming formulation, right? I mean, you cannot throw in more constraints, you cannot make it more complicated or more interesting.
Yes and no. No, in the sense that unlike Loewe-Schreiber and some other hierarchies, the degree D sum of squares hierarchy is fairly canonical in the sense that it doesn't really matter what particular set of polynomial equalities you started with for most problems. I mean, I'm in the sense that the degree D sum of squares hierarchy, for instance, for planted clique, would include every degree D inequality, that is, or equality. Sorry, every degree D equality that you could have added initially. So in the sense that it doesn't, unlike in case of Loewe-Schreiber, it was true that it really mattered what original relaxation you started with and you lifted. But here it really almost doesn't matter, in the following sense that there is no degree D inequality, or say degree D equality, that I think is true for integral solutions that you could add for planted clique. So
the parameter k doesn't appear in the statement? The size of the clique that you plan?
Over here, yes, it does. Sorry, I was being a little bit. So let's say, for planted clique, for k equal to n to the half minus epsilon. Okay, so this is the.
So you don't allow. I mean, so polynomial equations and inequalities are allowed, but no thresholding, no sort of
Yes.
discontinuous.
Yes.
Even simple operations.
Right, right. You know, this is for a very explicit program. So I shouldn't oversell it. This is really just for, you take the explicit program, which is the degree D SOS relaxation fortnightly, they prove a lower bound for it. It's not it's not a lower bound for general algorithms in any sense.
It's not a lower bound for the distribution distinction, for instance. I mean,
Yes, no, sorry. Maybe I'm overselling what I'm saying. All I'm saying is that we experimentally believe that these two distributions are computationally indistinguishable, and that should be useful in proving a lower bound for a specific algorithm. And this wasn't done earlier. Before this work, every lower bound proof went in this direction, where you just pick a random graph and try to prove that there's a feasible solution, which means that you throw away the planted clique distribution completely to the side, and then so the computational difficulty of distinguishing between the two distributions doesn't show up in the proof of the lower bound at all. Whereas over here, the proof of the lower bound actually uses the planted distribution explicitly, which is the key thing which I'm trying to emphasize. It's not that, this is not a lower bound against general algorithms. I'm just saying that you can,
So you're going to explain how it uses. Okay.
Yes, I will explain how it uses. Yeah, yes. Okay, so this is the idea, and we'll come back to this. I'll explain what pseudocalibration is a little bit later. But now that we are thinking about distinguishing between two distributions, as I said, this gives you a different way to look at LP SDP lower bounds, right? So in particular, so here's the situation. So we have two distributions. One is the planted and the uniform. Okay. You have two distributions. So we could, for example, decide to look at in some fixed distinguisher, let's say the degree of a vertex, okay, degree of a vertex. And then you could look at, this is a function, let's say D, this is a function, and then we would like to look at its expectation under the planted distribution, which I'll call mu in this talk, degree of a vertex, or under the uniform distribution, which I'll call nu. And then you could wonder if the two are comparable. And of course, if the problem is computationally hard, these two should be comparable. Okay, so this is a very simple distinguisher. We can go further. You could say, let's just look at low degree polynomials. So what do I mean by low degree polynomial? Here I mean low degree polynomial in the edges of the graph. For example, you could count the number of triangles in the graph. The number of triangles in the graph is a degree 3 polynomial in the edges of the graph. Right? So, and then you could wonder if the expectations of those quantities are similar. So let's say the low degree polynomial, P of G. The G is sampled from mu. Okay? And then you could try to prove that these two are comparable to each other. Okay? And this is a game we could keep playing in the sense that you could look at stronger and stronger distinguishers, and then in each of those distinguishers, we could try to prove that the expected value in one case is equal to the expected value in the other case. Okay, this is a very natural approach. And then you would have let's say D round Sherali-Adams LP here. Okay, and then you'd really want to prove proving a lower bound would amount to showing that the D round Sherali-Adams LP, at least in expectation, is equal to the D round Sherali-Adams LP for the two distributions. Okay, or you could do D round sum of squares SDP. Degree D sum of squares SDP. I will define what degree D sum of squares SDP is soon, but for now, just take it as an algorithm which outputs a number. Okay, And so we see that you want to prove, we could just look at arbitrary class of distinguishers and try to prove that their expectations in the two cases are equal. And
so why are you looking at expectations? Why is that the right thing to do?
So expectations, I guess, the simple thing to look at. Ideally, you would want something in probability. Yes, it's right. You're right that it's not sufficient that these two are equal in expectation. Ideally, you would also want to prove that in probability the distributions look the same. Maybe it is the case that if you look at the SOS value of degree D SOS value, it's an even number whenever it's a planet clique. It's an odd number whenever it's uniform. So we really want distributions. But for now, let's say this.
So you have this equally equal. You mean they're within 1 by exponential factors, 1 by Pauli factors?
I mean 1 plus 1 by Pauli, 1 by Pauli factors, 1 plus 1 by Pauli factors. Okay, so what's the point of doing this? Well, so actually let me add, so what's the point of doing this? The point is, maybe you don't want to think about Serrelli Adams LP or the SOS SGP. Let's just think about distinguishers which are general functions. And let's try to prove these indistinguishability facts for stronger and stronger class of distinguishers. And at some point, the distinguishers are so strong that they immediately imply Serrelli Adams or SOS SGP. Okay? So in particular, so in some sense, the main result of our work is the following, which I'll state formally later, but just to give you a preview. So look at the following types of distinguisher. So you compute. So this is called low degree matrix distinguisher. So the idea here is you compute a polynomial P, which is a low degree polynomial, but it outputs a matrix. So every entry of this matrix, so it's a low degree matrix polynomial. So every entry of this matrix is a low degree polynomial in the graphs. For example, this could just be let's say you have one row for every pair ij, one column for every pair kl, and then you put a 1 there if ij and kl form a bipartite clique. Right? So basically any matrix function whose entries are low degree polynomials in graph. So you compute this, and then you compute
What is D?
D is some polynomial size. So you compute I'm describing a class of distinguisher. So here's a type of algorithm you could try. You compute a low degree polynomial matrix of the graph, and then you compute its largest eigenvalue. Okay, this is an algorithm, right? You could just compute its largest eigenvalue, meaning you output lambda max, the largest eigenvalue of this polynomial, of this matrix. Okay, so now this is a very simple algorithm. We'll call this low degree spectral distinguisher. Okay, and essentially our main result is that low degree spectral distinguishers are as powerful as degree D SOS SGP for broad classes of problems. What that means is that if you're trying to run an algorithm for these distributional problems, in many cases, if your SOS SGP works, there's an underlying low degree algorithm which just computes a matrix and computes the largest eigenvalue. It's a much easier task than solving the SDP, which will also distinguish the two in the sense of expectation, not in the sense of probability. The other direction is if you're trying to prove a lower bound, all you would want to do is to prove that low degree matrix distinguishers don't distinguish between the two distributions. Okay.
This statistical query learning algorithm, it seems to be. I mean, you're just going to compute the eigenvalue.
Yes.
The eigenvalues are comparable with statistics.
I But we use a fixed graph in the sense that there's no, it's really like the algorithm takes the graph as input. So it's not statistical in the sense that you need the specific matrix to compute the.
Well, when you run the eigenvalue computer, whenever you want an entry, you can do statistical queries and get it. I think. I don't know. Yeah. It's an aside.
Okay. Yeah. Actually, that's one connection which I haven't explored. Yeah, which is these things do seem related to statistical query algorithms. And I am cheating a little bit here. Actually, lambda max is not lambda max. It's lambda max plus. So what is lambda max plus? That is max of lambda max and 0. P of G. Okay. But this is essentially the result, but I'll describe it in greater detail. But the reason I really like this kind of presentation is that when you state the problem as trying to come up with a SOS solution for a particular graph, the problem becomes very hairy with all sorts of equality constraints that you need to satisfy, and a very hairy problem with, we did not construct this thing. Whereas when we state the problem as there are two distributions and you'd like to prove that a function like this has the same expectation under the two distributions, this seems more well-studied, a little bit more well-studied in the sense that this is essentially what happens in a lot of pseudo-randomness work. When you say bounded independence fools half spaces, what they're proving is that you take the uniform distribution, you take a distribution which is bounded independent, and then you take your function to be a half space, the expectation of the two distribution is the same. And if one could do such things for functions which are like this, which are spectral, that would be fantastic, because then that would give you a more cleaner way to get all of these lower bounds, given this result. Okay.
So, are you claiming that this method is equivalent to SOS, or that many of the results that you get with SOS you could get with this spectral method?
Essentially equivalent. I'll prove it. If I have time, we'll see a sketch of the proof. But I'll state the theorem. I'll state the theorem in more detail. So yeah, sorry about
Just make this clear. So this is in the statistical case. I mean, for any instance, there could be. I mean, I guess.
Yes. So it is a little bit. It's a little bit statistical in the sense that the two, we are just claiming that the expectation of the two SDP values are the same. But if you really want to prove that they're indistinguishable, you would want some sort of high probability statement. But in some cases you can get this just by Markov inequality. For example, if you are interested in planted clique, if you prove that the expectation of the SOS SDP value is root n, then with at least 1 over poly probability, it's at least so in that sense it's okay. So now I want to state the result. So in order to state it, let me just define some notation. And so in order to write a SOS relaxation, what we first need is a system of polynomial equations. So for example, if you look at this planted clique problem, so here's the system of polynomial equations that one would write down. So each xi, there's an xi variable for every vertex, and this variable is either we expect it to be 0 or 1. That's our goal. So we first add a constraint which ensures that xi is 0 or 1, which is the Booleanness constraint. Xi squared minus xi is 0. And then we want a clique of size k. Therefore, summation xi minus k is equal to 0 is a constraint saying that there's a clique of size k. And then we want it to be a clique. Since we want it to be a clique, whenever there is an edge between I and j, xi xj should be, sorry, whenever there's no edge between I and j, xi xj should be 0. So ij is not an edge, implies xi xj is 0. Now, the function, whether ij is not edge, if ij is an edge or not, is actually a low degree function of the graph itself. If gij represents, if gij is, let's say, plus minus 1 random variable. Is a plus minus 1 value, and such that Gij is equal to 1 if ij is not an edge, and 0 otherwise, sorry, minus 1 otherwise, if ij is an edge, then this constraint precisely encodes the fact that whenever there is an edge, whenever there is no edge, xij is 0. So that's this.
The opposite. It's minus 1 if ij is not an edge.
Oh, yes, yeah. Thanks. Yeah. Okay. Yeah. Yes. So, but the key thing is that we have a system of polynomial equations, and each of these equations is low degree in X, that is of course true, but also low degree in the graph G. Right? As a function of the graph G, each of these equations, the coefficients in these equations are low degree polynomials. Okay. So whenever we have a polynomial system like this, we can write sum of squares SGP relaxation, and the sum of squares SGP relaxation, if you were to state it succinctly, what it does is it tries to look for a refutation of the system of equations. So what it does is it tries to look for an identity of the following type. Here, remember that Ej are the equations, Ej of x comma g are the equations for any graph G. And the sum of squares SGP tries to find an identity of this type where -1 is equal to summation, sum of squares of polynomials plus polynomials which plus a term which is in the ideal generated by the Ej's. And the entire identity includes only polynomials of degree at most 2D with the squares.
Those also depend on the graph.
Yes. Good point. Thanks. Yeah. So I should write. I should, these depend on the graph, but yeah, these depend on the graph. Essentially, when you pick a graph and run the degree D SOS algorithm, it looks for an identity of this type, and
X comma j in G.
yes, yeah. In Ri, I could write x comma j, but I could write this as Ri of x comma g. But I haven't written it that way because a priori it's not clear that this is a low degree function in graph G. Therefore, I didn't want to allude to that by including it here. Here, this is clearly low degree in G, but these are arbitrary functions. Basically, you take the graph and solve the SOS. You might get some Ri function of G. For every graph G, there is some Ri of G. Yes, which is yes. Okay, so a question. In some sense, every function on G is a polynomial in G. It's a degree n polynomial because it's just Boolean hypercube. But yeah, you're right that they're not really legitimate polynomials in the sense that they're not low degree or anything. They're just arbitrary functions of G. Okay, so now I'm ready to state one of the key conditions that we need in order for our claim to be true. So here's the condition. We call it the robust inference property. Maybe there's a better name. So here's the property. So let mu be a probability distribution of 0, 1 to the n. Think of this as mu is the planted distribution. Okay, you have a planted distribution on 0, 1 to the n. Actually, before going through the claim, let me just say in words what robust inference is. Robust inference property is the following. If you get a sample from the planted distribution, we know that there is a solution to the SGP or the polynomial system. But what we really want is something stronger. If I give you a random subsample of the vertices of the planted distribution, even then, just given that, we should be able to recover a solution to the SGP. So it will be very clear. Maybe before the definition, let me just go to the planted clique case. Okay, what is true about the planted clique case? If I look at this polynomial system, let's say, let me write this as summation xi is equal to r, xi squared minus xi is 0, and then the other condition. if I look at this polynomial system, if I give you G from planted distribution, there is a solution to this system. That is obvious. But even something stronger is true. If I just gave you, let's say, half the vertices of the graph G, you can just, looking at those vertices, construct a solution to the system, because what you could do is you could just output the clique vertices that you see inside the set. So here's the setup. So imagine you have this. So this is the graph G, okay, and let's say this is the clique that we planted. Okay, it's a set of size root n.
So how is R related to K?
Yes. So yes, right to the point. So suppose this set is size root n. Of course, R should be smaller than K, because we only know that there's a solution for plant clique with equal to K. And so R should be smaller than K, but let's say R is much smaller than K for now. Let's say R is epsilon K. Okay, let's say R is epsilon K. Let's say R is delta K. Okay, R is delta K. Okay, so here's the fact that's true. If I give you, if I subsample this graph by just picking each vertex in with probability, let's say 2 delta. I take every vertex, I throw it out with probability 1 minus 2 delta, I keep it with probability 2 delta. I get a subset of the graph. And this, we expect, will contain some of the clique vertices and some vertices outside. This is a 2 delta fraction of the graph, just randomly subsampled. Now, even just given this random subsample, G sub S, one can construct a feasible solution for the original polynomial system with high probability. Right? Given just this G sub S, one can construct a feasible solution for this polynomial system just by, because the clique will also contain, there'll be delta fraction of the clique also falling into this random subsample. You just set those xi's to 1, and you get a solution to this system. Okay. Is this clear? So.
Is this S the same as the S in the
no. This S is. Oh, this S is the same. This is the planted disk. Oh, yes, sorry. G sub. Yeah, sorry for that. So G sub T. Okay, we sample a random subset T. Yes. So this is just saying that if you have planted a clique, then you'll not, you'll actually see the clique in any subsample also. You don't need the entire graph to see the thing. Okay. So this is essentially what we call robust inference. Okay, and so this is it claims you have a planted distribution and you have a probability distribution over subsamplings of this, and for which is basically in our case you just pick every vertex in with probability something and out with some probability, and we say that the distribution satisfies robust inference property with respect to this subsampling if mu is epsilon robust inferable with respect to this subsampling if you can infer a feasible solution to the system given just the subsample. Okay, that's okay, and this does seem like a very strange condition for now, but I'll show examples to prove to you that it's not that strange. It's just some sort of noise. It's some sort of robust inference. It's just some sort of noise. So instead of going through the definition, let me just give you a bunch of examples. Yes.
So what do you mean a solution for the system? The system is a pair of things. You have a solution that's the same for both? What's the... If you go back to your definition slide.
Right. Yes. The solution to the system for the system is a pair of things, as in?
Set H to be a pair.
H is a pair. So let me parse this. So essentially, you take a graph from the planted distribution, okay, and then you subsample the graph. You subsample a subset, And then I'm allowing you to take the rest of the graph and modify it to arbitrary, anything you want.
Okay.
And then you get a new graph H. What should be true is that just by looking at the original part of the graph which was left, you should be able to infer a solution to the polynomial system for H. So this is a robust inference property. So why is this not very strange? Well, it's somewhat very it's pretty easy to find this robust inference property. For example, suppose you wanted to prove a lower bound for planted clique, for max cut, let's say a linear programming lower bound, or you want to prove a lower bound against community detection, which is stochastic block model. There are two distributions which look like the following. In one case, you just have a uniform distribution over sparse graphs, which are sampled with G, n, B over n. In the other case, you have a planted distribution, which look like the following. You have two sets A and B of equal size, and the probability of adding an edge across is A over n. The probability that adding an edge inside is B minus A over n. Basically, the two probabilities are different. The probability of intra-cluster edges and inter-cluster edges are different. And you would like to find out which of the two cases it is. And by fixing A and B appropriately, you can sort of pose this as max cut and all sorts of things. Okay, so what is the polynomial system I'm talking about here? You would want to find a vector which is plus minus 1. You'd want to find a plus minus 1 vector, which is which side of the partition each vertex falls in. And the system is just going to be, let's say if you know that half the vertices fall on each side, so summation xi is 0. Then you would want xi squared is 1. This is just xi is Boolean. And you would want, the key thing is you would want to correlate with the probabilities as much as possible. So we could just state this as x transpose Ax is bigger than some quantity rho, where A is the adjacency matrix. So this is the sort of polynomial system that you would write. It's just, all we're doing is you're trying to correlate with the graph as much as possible. So this is a polynomial system. Okay, so so now we need, so what are the variables now? The variables, you get a graph, so you see the edges of the graph. Okay, and what's the subsampling that we'll do? So I think the subsampling that we can do here is essentially the same. So we take, but with edges. So we take every edge, and then we include it with probability 1 minus delta, and we throw away the edge with probability delta. Okay, the subsampling is include each edge with probability 1 minus delta, and throw away the edge with probability delta. Okay. So this does give you, this is clearly a subsampling of the graph. What is true about this is that since we kept most of the edges around, because we kept 99% of the edges around, you will lose only a little bit in the correlation with the adjacency matrix. Okay. If you were correlating 1 minus epsilon with the adjacency matrix, now you would correlate 1 minus epsilon minus delta. Okay, so you lose just a little bit in the correlation. Over here, what that means is when we wrote down the polynomial system, we should have put in some slack here, so that even given just the edges from the subsample, should be able to reconstruct a solution which is pretty good for the entire graph. Okay. So you see that this happens here, and essentially the same kind of subsampling can be used for random 3-lin. Okay, random 3-lin or any random 3-lin, you could do random 3-sat or any CSP basically. It's just the same, essentially the same idea. The idea is you have random clauses which are appropriately chosen, and then your subsampling is just throw away a delta fraction of the clauses. So you lose a little bit in the value, but it's still it's still reasonable. Okay. Okay. So it's a very general theme. This sort of happens in tensor PCA and many other problems where where you have a signal which is so robust that even a subset of the entries should reveal the signal. It's just that computationally it's difficult to find a signal. And this is true in tensor PCA. I won't define this problem, but just I wanted to show it for people who have seen that. Okay. Okay, it looks like it looks like I won't be able to say much about the proof, too much about the proof, but at least I will try to explain what pseudocalibration is by the end of the talk. Okay, so that's the goal. So now I think we're ready to state our main theorem. So the main theorem is if you have any polynomial system which is degree d in the xi's and degree k in the graph. Degree d in the xi's and degree k in the instance. Okay, you have some polynomial system. And it's very robust. So this is the probability with which you'll fail to find a feasible solution when you subsample. So the probability of not finding a feasible solution should be extremely close to 1, extremely close to 0. B is some number which is just larger than d and k. So just take this to be more than 2dk. Just any number which is larger than d and k. So one property you need is that it's you can robustly infer solutions from subsamples. The second property you need is that the SOS refutations have fairly nicely bounded numbers. So the SOS refutation, for example, in planted clique, whenever there's no clique and there is a refutation, the refutation should have numbers which are polynomially bounded. And this is something which you need to prove in case by case, but it is always it's almost always very easy to prove this fact.
Are you assuming there's an SOS refutation with this bound, or you're saying every what's the statement?
Assuming there's an SOS refutation. Okay, so okay, what is the main theorem saying? Actually, I should just say it in words. Firstly, it's saying that if you have SOS refutes or distinguishes between the two distributions, then this implies that the spectral algorithm also distinguishes. That's the claim. Yes. Sorry, why is this happening? Okay, so the spectral algorithm also distinguishes. That's what we are claiming. So we are assuming that there is SOS distinguished between the two, and let's say we assume that it distinguishes with numbers which are bounded. Okay, in this case, we can prove that there is a degree capital D polynomial that actually also distinguishes between the two cases in the following sense.
Right on the board.
Or maybe it's the airplane mode.
Maybe you need to charge the battery.
No, it's very well charged. It's just yeah, it's okay. Sorry, I'll write on the board. It's strange. I teach with this every week, twice a week, and never. So somehow in Simon's it always fails. So this is the statement. You sample the graph from the planted distribution, and you evaluate this function, which is basically the largest eigenvalue truncated to be positive. And you look at the ratio of these two quantities. This is the uniform distribution. This is the planted distribution. Okay. There exists a low degree matrix polynomial such that this ratio is very large. Yes.
So is this for k n to the half minus epsilon, or?
Well, this theorem is actually very general. It applies to all the settings that I described earlier. So for three lane, and it's just to say, like, the theorem has nothing to do with planted clique. As this, it's just any polynomial system, and this is just true. So in particular, it also applies to
robust verifiability holds for k.
Oh yeah, robust verifiability is just it holds for basically it holds for whenever k is large. This is a claim. So you see that it shows that the two expectations are very much off under the two distributions, and
Prasad,
yes.
You don't need anything about the degree of the SOS refutation?
I think we overloaded notation and used D for both, in the sense that if you're anyway solving degree D SOS program, you may as well assume that you had your original system was also degree D, because you can add every so here D is, you could think of D as the little d as so what I didn't tell you is how this capital D relates to little d. Okay, and that is over here. Essentially, you want the capital D such that if I pick any subset of capital D coordinates, the probability that all of them fall in the subsample is very small. So that is the thing, and so this clearly differs from problem to problem. In for example, in max cut or in the community, we were throwing out every edge with probability delta. So which means that if you pick a subset of edges of size L, subset of L edges, then the probability that the whole thing falls inside is 1 minus delta to the L if you keep every edge. So this is, which means that you need to pick capital D to be really large for this ratio, for this probability to be really small. So it's going to be D log n. So for max cut and so on, for max cut or the community stochastic block model, over there capital or all the CSPs, capital D will be D log n. So what this is saying is that if you degree D sum of squares programs are just as strong as polynomials of degree D log n. Okay, which but if you look at planted clique, there the subsampling is very harsh. You actually can keep every vertex with probability 1 over n to the point epsilon. You'd still have a plant clique of size n to the half minus epsilon. If you start with a clique of size n to the half, if you kept every vertex with probability 1 over n to the epsilon, you still have a clique of size n to the half minus epsilon. So it's very strong subsampling. In this case, capital D will be much smaller. Capital D will be essentially be order little d. Okay, so that's I'm assuming that Sleel, who's in the audience, will correct any mistakes that I made. So if she's quiet, which means I'm okay. Okay, so I think we have about 5 to 7 minutes. I think the key thing I'll try to do is to actually show what I promised, which is pseudocalibration, to tell you what pseudocalibration is and how our idea goes along with that. Okay, so here's a quick. Okay, forget it. So what is pseudocalibration? I think this is a very beautiful idea when I think you know, the one way to advertise it is it gives you a mechanical way to construct LP and SDP solutions for these problems. Once you have the two distributions, it gives you a very mechanical approach to construct the feasible LP SDP solutions. And then, of course, proving it is feasible is the tricky part, but it at least gives you a candidate solution. Okay, so here's the idea. So if you have mu, which is a planted distribution, I'll call it the planted density. So mu is a function on, let's say, graphs. So what you have is, okay. So this is a planted density, and you know, the way to think of this is, on most graphs the planted density is 0, right? Mu of g is 0 on almost every graph. On an exponentially small fraction of graphs which are actually coming from planted distribution, this value is really large, so that the expectation is 1. This is just a planted density. Okay. And let's say, you know, for every graph which comes from the planted distribution, we know what the solution is. It's just a clique, right? There's an integral solution we can write down. So let's just write down that function. I call this lambda. This is a function from graphs to, you could say, let me just say, some high dimensional space. This is just the space where the feasible solutions live. So if you have a LP, it's just a vector of all the values of the solution, and if it's an SDP, it's a matrix, but it really doesn't matter. It's just for every graph you want to write down this. So what is the definition of lambda? So lambda of a graph G is just, if it is not a planted planted graph, then you don't know what to do. You're just going to output 0. 0 outside mu. Okay, but really on mu, when it is a planted graph, it's equal to mu of g times the integral solution for g. Right, we can actually write down an integral solution for g. It didn't have to be integral, it just had to be feasible. But basically, we can write down an integral solution whenever it's a planted graph. So this gives you a function. So this gives you a function from graphs to, let's say, SDP solutions. And it's a very not a useful function a priori, because whenever on most graphs it just outputs 0, but on planted graphs it actually outputs the integral solution. Okay, so now if you think about this graph, it's this function. It's as I said, it's really on most graphs it's 0, because and only on the planted graphs it outputs an integral solution. And there's a large multiplier which comes from this mu of g, which is supposed to be like the 1 over the probability that your graph is planted. Okay, so far it's all fine. And then what does pseudocalibration do? You take this function lambda and you truncate it to low degree. I have 5 minutes. So you take this function lambda and you truncate it to degree capital D. Okay, it's degree capital D in G, in the graph G. It as a function of the graph, it was an arbitrary function. You just take its low degree part. An alternate way to say this is you're just projecting lambda of G to the low degree, to be a low degree function. So now this is a function now. It's a legitimate function on graphs, and it's not going to look like this, because low degree polynomials cannot look like this. It's going to look more evened out. Okay, and this is the candidate SDP solution, SDP or LP solution. Okay. Meaning on a random graph, you just substitute its value, substitute a random graph here, it gives you some matrix. That matrix is supposed to be the LP or SDP solution for that graph. Okay. So you see that it's completely mechanical so far. But what is the advantage of looking at this object? One particular advantage is, first of all, you can show that this immediately almost immediately satisfies all the equality constraints of the SDP and LP. All the constraints which come from the problem are almost already satisfied. Why? Because lambda of G satisfied all the equality constraints, because it's actually a valid solution on every graph where it outputs a solution. So it's a valid integral, so it satisfies all the equality constraints. So it's very easy to show that this object satisfies most of the annoying constraints that come about. So the only difficult part, which we still don't know how to do very well, is to prove that this is PSD with high probability over G. Okay. This is essentially pseudocalibration. So it gives you a mechanical way to construct LP-SDP solutions given two distributions, which are supposed to be indistinguishable. Okay, and now I think in 1 minute, what we do is, one way to say what we do is, instead of taking lambda and projecting it onto low degree space, we take lambda, which is lambda is nice and PSD also, right? Lambda of G is PSD everywhere. It's a PSD positive semi-definite matrix at every graph, just because it's a valid solution, and so lambda is it's PSD solution. What we do is we just try to find. So since we try to find the maximum entropy projection, instead of just L2 projection. Instead of taking lambda and just truncating all the high degree stuff, let's find a PSD valued function which has the same low degree properties as lambda, but is as flat as possible. So we have, so the idea is essentially we have this lambda which is very spiky. What we want is another function, lambda star, okay, such that if you look at the low degree part of lambda and lambda star, they are the same. Okay, the low degree part is the same, but lambda star is has maximum entropy, has higher entropy, or you could say has bounded 2 norm, is more flatter. Okay, and so that's the idea. So in matrix land, it might be a little bit more tricky, but in terms of distributions, here's a way to think of distributions. So you have the planted distribution, which is just a function which is really spiky. We ask the question, can you find a different probability distribution on graphs which has the same low degree properties as the planted distribution? On the low degree functions, it looks the same, but it has as much entropy as possible, meaning has as little spiked as possible. So that's a convex relaxation. Finding the maximum entropy distribution is a convex relaxation, and what we do is we just say, we write down the dual of it. When the relaxation has no solution, it means that there's a spectral distinguisher. Sorry, I didn't have time to explain that very well, but I'd be happy to explain it later. I think I'll stop here. I don't want to go. Yeah, I'll stop.
Can you elaborate on that last sentence? You said, well, if there is, if you look at this max entropy distribution, then the dual of that is.
Oh, okay. Yes. If you write down the convex program, which is find the max entropy distribution that agrees with lambda, the dual of that exactly gives you the low degree spectral distribution. So it's really.
I mean the spectral distinguisher that you suggested?
Yes, the low degree spectral distribution, that Q that I was talking about. So let's say you want to minimize the 2 norm of lambda star subject to lambda less than or equal to d is equal to lambda star less than or equal to d. The low degree parts are the same, and lambda star is PSD. Okay, this is a convex program. If you write the dual, it's going to be a maximization problem, right? And it's just going to be something like find a low degree matrix polynomial that correlates with the planted distribution too much more than it does with the uniform distribution.
Prasad, maybe it would be good to write the equality constraints in terms of this Q, because then it will be really obvious why these will.
Yes, right. But if you trust me, these are duals of each other. But one way to write that the low degree parts are equal is to say for every polynomial Q, lambda inner product Q must be equal to lambda star inner product Q. Okay, that's the same as writing that the low degree parts are equal. Okay. Now it's clear that if there is no solution to this program, there should be some Q which actually distinguishes between the two, and that Q will be the matrix distinguisher. So it's really very it's simple. Yeah.
So that's zeros. Those zeros over there. This is just for convenience. Somehow it's really completion thing, right? I mean, you're allowing there to put anything.
Oh, here?
Yeah.
No, I think 0 is somehow crucial, because if you just look at one entry of this, you want it to look like mu of g. Right? Like, let's say in the SDP solution, for instance, there is one entry which corresponds to 1, right? And just like, and that should essentially look like a density. So if you put other things, then this won't look like a density anymore. Yeah. So 0 is important because we're taking low degree projection of this matrix. And so if you put other things, then the low degree projection will be different.
Okay, now let's thank you.